Thank you. I'm Matt Bauman. I work at Julia Hub, and I'm going to be talking about some things that I've been chipping away at for the last 2 or 3 years now, about why some functions are extremely hard to get right, or really why some functions are extremely hard to get right. The core challenge, it doesn't seem like it should be hard, right? We're just adding numbers together. This is how lots of tutorials start, but hopefully you're all cringing at this. This isn't how we should write this, right? We know better than this. We're a dynamic language. We don't need to hard code types. We can say it's an abstract array. We can change the beginning, the initialization of how we do this addition. We can even support non-arrays just by iterating over things. We can add SIMD annotations to get better performance here. We can even abstract this away more to call it a map reduce, which is just saying hey, we have this operation, it's plus operation, and because Julia optimizes over the function types, this is all we need to write, right? It's very simple, but Tim Bizard actually set this up perfectly if you were at his talk just an hour ago, because he simultaneously showed that a sum function can output to 5 assembly operations without any function calls, just 5 assembly operations, but then also said it's really hard to implement a reduction on a GPU. And on a GPU, you're actually in a much more constrained case because you have a limited set of types. You're much more homogeneous type environment generally. So there's a lot of things actually that this makes this hard. I have 7 here that I want to go through and kind of think about with you all about why this is hard and how we can make it potentially more robust. But first, let's talk about what are the rules here. What does a summation mean? What do we need to do in order to do a summing sort of operation or a reduction? And really, I'm using summations here as kind of the example reduction operation. Anytime I say sum, you can think of any reduction operation. It's just we happen to be using a plus operation here because it's the cheapest one we have. And so if we can make that one fast, then that means that we've reduced the overhead in doing all sorts of more complicated things. So all we want to do is take a collection of many items and get a single value out of it by doing a lot of pluses, right? Very, very straightforward. Seems like it should be straightforward anyways, but we need to keep the ordering the same. You can't arbitrarily reorder, so I can't put the third element before the first element. That's pretty standard. We can't assume that our operations are commutative here. But we do say that a reduction can do an arbitrary associativity. So you could start at the left and add the numbers going to the right. You could start at the right and add the numbers going to the left, or you could do something weird and in between. And the reduce function in Julia is the sum operation, the prod operation, the maximum, minimum, the extrema, all of these. They say we can choose the best associativity here. We don't guarantee any associativity. So that's great. It also is very explicitly calling a 2-argument function, right? You could call a plus operation with more than 2 arguments, but reductions need to take a 2-argument function. There's a less obvious rule of the game here that we didn't really figure out until about a year or 2 ago, which is what the init keyword actually means. And it's kind of surprising that we haven't figured this out, and the documentation still hasn't been updated here. There's an open pull request on this, and the reason that it's still open is because the base implementations don't fully comply with this yet. We need to make sure that the base implementations actually do what the documentation says they'll do, but that's what's happening. And what it means is that every time you start a chain of operations, you want to use that init value to begin it. And so it's kind of the initialization. It's not your offset, right? So this one kind of, the biggest trouble here is that if you're writing sum A init equals 100, you kind of think of that as being 100 plus the sum of A, right? Like that's kind of how that reads, but that's not what it means actually, and that's not what it should mean, because you could use init multiple times if you have multiple parallel chains. And the reason that this is important is partly because of GPUs, but also partly because we care about type stability. Init is important for that purpose. And it also helps cement some of the rules of the game, and that you can then count on the fact that if you're passing init, you always get at most one argument from the collection in your operation. And then the other argument is either going to be an init or the result of an addition operation. So it kind of cements a few of the games there, but it is a little tricky. And in fact, some of the examples in the documentation used to have things like sum A with a non-zero init. So why is this hard? Let's go through some of these things. I'm going to tackle these first 2 points somewhat together because they're highly related. And it is exactly that initialization point and how it relates to the 0 and 1 element case. So one of the reasons that we have the init keyword is to handle an empty case. So if you've ever called a maximum or a sum on some weird type and got an empty reduction error, that's because we don't know what type to give you back if there's nothing to add. You don't have anything there, and so we don't know what to give you. And so without giving an init, you'll either get an error, or in some cases, we can say, oh, okay, with the plus and a sum, we know that you're going to get a 0 of some sort. With a multiplication and a prod, you're going to get a 1 of some sort. So in some cases, we can figure out, okay, this is an obvious value. We can do that. That's governed by an internal function called MapReduceEmpty. If you have one element, well, then that element is the element itself. And this can lead to some surprises here too. Most commonly, I've run into this myself with VCAT, because VCAT will either return an array, or then if you're reducing over it, well, it's going to just return the element itself. And so then you end up with not an array if you don't have an init value there. That's often where it comes up. So that's troubling. But then if you have init passed, well, then the 0 element case is easy. That's the init itself. And if you have one element, well, then it's init plus that one element. That kind of simplifies this. And this is kind of the prescriptive view of the world. It's not fully consistent, not yet. But this is important for type stability, right? We need to be able to know that inside of those loops, we have a type stable thing. We want this to be fast, and to be fast in Julia, we want it to be type stable. And so that's exactly what these internal functions are trying to do. MapReduceEmpty tries to ensure a type stable neutral element that is not only type stable inside the loops, but also as an outside the function as well, right? The values that you get back from the function, we also want to be type stable as best we can. So that way, when you work with them, you don't run into catastrophic problems. These have gotten better in the last few years, though, with union splitting. It's not near as troublesome to have, a small union, which is what typically ends up happening in these cases. So yeah, the other thing that's a little tricky here is if we didn't pass init, and we have many items and we want to start many subchains, we need to make sure that every time we start a subchain, we have at least 2 elements. And that becomes important later on. Let's talk a little bit about floating point accuracy. That's another thing that makes this hard. And it kind of simplifies some things, but makes some other things more challenging. The biggest thing with floating point numbers is that associativity matters. And my favorite example of this is a thread that Stefan Karpinski posted on the discourse board about how if you have an array of about 2,000 elements that are well chosen, you can make them add up to basically any floating point number you so choose just by changing the ordering or not changing the ordering, changing the associativity of them. And so it is the ordering. I'm sorry, I got that wrong. So yeah, by changing the ordering of your summation, you can change the values you get. And the same is true with associativity. It matters greatly here. And the goal is to balance performance and your typical accuracy. The accuracy you get is also data dependent, but generally the best accuracy you can get out of a generic summation without doing work on the data is compensated summation, but that's slow. That requires lots of extra operations. It's also not generic of a reduction sort of operation. It's very tailored to floating point addition. Next best is a full pairwise operation, right? Where every step along the way, you take two values and add them together, and you do kind of a full binary tree down to the end. So you have A1 plus A2, and then A3 plus A4, and you add those two values, and then you go on and you keep getting bigger and bigger numbers that way. That's also typically slow, or at least has been. Newer processors are actually adding pairwise intrinsics in their SIMD units, which is cool and interesting, but doesn't do the full thing. It's just one SIMD width wide. The next best is to do a pairwise addition of some larger base case. So the example here is a base case of 4. This is what we currently try to do in many cases, or in some cases, it's what NumPy does. You pick some base case that works pretty well for performance purposes. So, you say you add 100 numbers and then you do binary addition from there on out. Or pairwise addition from there on out. A bad choice, though, is the straights left to right, fold L or fold R. That's what we call the straight left to right. It's bad for accuracy, but it's also bad for performance because of the way modern processors work. They like to work ahead if they can. And if you're always adding things into the same bucket, they can't do any sort of, work ahead with pipelining and things like that. It also it's a poor choice, not just for accuracy, but also for performance. So are we pairwise yet? Do we have these pairwise capabilities? And no, we don't. And right now we fall back to that worst case, that fold L in many cases, includes iterators, generators, index Cartesian arrays, which are a lot of wrappers and a lot of views. And this is actually how I got started on this. Jorge posted an issue that said, hey, my mean across a view is a different number than a mean of the array itself. Why is this? This seems wrong. And it's because of this issue. It's because that mean didn't use pairwise summations. This is especially egregious across dimensional reductions, which we'll get to. And all of this means that the accuracy you get out of a simple function like sum is dependent upon many factors: type stability, the wrapper types, the memory locality. All of that matters, which is quite surprising. Let's talk a little bit more about performance and SIMD in particular. The good news is SIMD improves floating point accuracy. It rearranges things, instead of just adding one bucket, you have multiple buckets that all get added together, and then you add all those buckets together at the end. The bad news is that it improves accuracy. It changes your answers, right? And what makes that especially bad news is that SIMD is highly sensitive to optimizations and type stability, right? So if you have a bounds check, you're not going to get SIMD code. If you have a type instability, the SIMD macro is not going to give you that. It's leaning on the compiler to do it if it can, if it feels like it. Don't know. Maybe it will, maybe it won't. It also doesn't work for iterators. So it would be nice to do this more consistently and try to get SIMD both for accuracy and performance without leaning on the maybe it will, maybe it won't kind of thing. And in fact, we do get to choose the associativity, right? That's the rule of the game. So we could choose to pick an associativity that works well for SIMD and just always use that. But optimal SIMD use actually changes the ordering, which is one of the very first things that I said you can't do, right? You can't change the ordering of the operation. It's one of the things we guarantee. And that's what happens. And this actually took me back. I'd long known how SIMD works. I've long even described this in trainings as like, you sum into different buckets and then you add the buckets together at the end. And, I've said, well, it's because it reassociates it. No, it actually does a commutivity. It recommutes the operation. It doesn't reassociate it. And I think I got thrown off here because the typical compiler flags here are called reassociate, right? Like you reassociate it, and that's what enables a SIMD. And yeah, it does, but the compiler knows that, oh yeah, floating point addition is commutative. And so if you enable associativity, then it can take advantage of commutivity as well. But it's actually commutivity that's giving us the best SIMD use cases. So that one, like, I couldn't believe I didn't really process the fact that SIMD requires commutivity in order to get the best performance out of it, even though I'd known it at some level. So what do we do about this reordering, right? Ideally, we would allow things to reorder things. And we could assume that plus is a commutative operation. Maybe that's what we should do. We don't document that though. And it's not actually true for some algebraic types. There are types that don't do this. And we kind of say that you can do anything with plus. You just define a summation operation. And but it's undocumented. It's not clear. It's also challenging because we don't really know at a fundamental level what types are going to be adding these things here. And so like it could be reducing over in any array, and we don't want that to have significant changes on the accuracy, right? Or I wouldn't want that to have a change on the accuracy. So you can't really dispatch on, plus of two floating point numbers. We also don't know what the output of plus is going to be. Maybe that'll be a floating point number. Maybe it won't be. This is one of the challenges of generic functions is they can and they do often do anything. The one interesting point here, though, is that doing this reordering can improve performance even when the processor doesn't actually use a SIMD intrinsic. And this is precisely because of the complexities of crazy modern pipelining processors. But that, by reducing the chain of the pipeline, you can actually get much better performance. So I don't know what to do about this. It would be interesting to kind of play around with, like, maybe we want to assume that plus is commutative, or we could also say that the plus operation that sum uses, which is actually slightly different. We have an internal add sum function that enables some other functions. We could say that one in particular is commutative, and that would help with the sum function itself, but it wouldn't help with other things. Not sure. What else makes this hard? Well, there's the fact that we have iteration, we have indexing, and we have all sorts of generic implementations, and there's lots of things that find their way through reductions. Iterators themselves don't support SIMD. They actually can have two flavors. Maybe they know their length, maybe they don't. And pairwise summations with iterators isn't an obvious operation. It took both Stephen Johnson and myself a while to realize that it doesn't actually require arbitrary random access into the array to do a pairwise reduction, which should, again, one of those things that in hindsight is like, oh yeah, that should have been obvious. But no, we can do that. You don't need random access into the array to do pairwise summations, but it's a little tricky to structure your code well. And it's even harder if you don't know the length up front, because remember what I said about initialization. In some cases, you need to make sure that you'll always have two elements in your array to start the next chain of a pairwise summation. And so you need to kind of peek ahead on an iterator, which is also an operation that's annoying and challenging to do with performance in Julia. So that's hard. There's also all sorts of complexities around all the things that people expect out of a reduction and the guarantees that we should or maybe should not provide. we talked about commuting plus, or how about max and min? Should we commute those? Those are commutative operations. Is init always going to be a left argument, or is it sometimes a right argument in the two arguments of the operation? Could you potentially call either the mapping part of MapReduce or the reducing part of a MapReduce speculatively to kind of do some optimization? Maybe you want to memoize it for some sparse data structure. Is there an interface that an array could implement to get faster reductions? Like, all of these things are hard. And this kind of leads me to the point of but what about transducers? Transducers are cool. Like, can we just implement MapReduce with transducers? And it's actually a little bit the other way around. We need a solid implementation of MapReduce in order to use transducers. You need to know the rules of the game in a really strong way in order to use transducers, because what transducers do, if you're familiar with them, there's lots of really cool stuff in the Julia world with transducers.jl. What they do is they put more of the computation into the reduction operator itself, or the mapping operator itself. But in order to do that, you need to be really sure that those operations aren't speculatively executed or memoized or any of these other things. And if we don't have those guarantees well set, then the transducer is not going to do what you want it to do. The last thing that really makes this hard is dimensional slices. And this is perhaps the worst one of them all. That's where most of the challenges in the base library are, because dimensional slices allocate an array. And you need to know the element type of the output that you get. And this is the classic problem of Julia. You're doing array operations. You need to figure out what the output element type is going to be. And it needs to get that element type right. And this should be incremental widening. We don't do incremental widening for dimensional reductions here. But we should be able to be prepared to get a wider value or a different type at some point along the reduction way. So that would be the ideal way of structuring it. But it's hard to do that, especially hard to do that in a performant manner. And the rules of initialization run counter to what we often do, right? The typical Julia idiom of defining your out-of-place operation as the copy of the in-place operation. Or, you have your sum defined in terms of your sum bang, where you just, figure out what's the good init value for this, and you do the sum bang into that good initialization vector. But we can't do that in this case, because how do you initialize a vector? Well, it depends on, is there one element in the array, or is there no elements in the array? Is there two elements in the array? Did you pass an init? All of those things change how you end up initializing that array. And in fact, you need to peel one element off of your array in order to do that initialization. And to do that peeling operation, or to remove that from the rest of it, ends up being far more complex than just doing the dimensional implementation without trying to do this composition. And so this trying to figure out what the initialized array to do an in-place operation in is where 90% of the bugs in the reductions come from, is getting that guess wrong about what your initial value is going to be. And then if you get the element type wrong, maybe you do a conversion that's inappropriate, or you just get the wrong answer in the first place. So lastly with this is the fact that we want dimensional reductions to be cache efficient. And this is why we can't just use each slice here. If we just did the sum of each slice, we would do something that's terribly cache inefficient, which is a performance penalty often on the order of 10 or 100-fold. And so we have a faster cache efficient mechanism in base right now. And if we were to just rip it out and throw this away, we would have a huge speed bump. So can we do better? Yeah, we can. It just is going to take some time and effort. I have 2 open pull requests to Julia right now that have been languishing. I worked on it a good amount in the spring when abstracts were due here, and haven't touched it much since. The two big ones are to get the empty case behaviors correct between both, the scalar and dimensional reductions, and then making sure that everybody uses pairwise everywhere. So that's what the second one is. The second one is the big one that requires a lot of changes. It drastically changes the implementation that lots of array types have been overloading without there being a well-defined interface here. But so it's hard, right? Because it's breaking to those in the arrays that were doing the thing of extending a private interface or a private function. But what this pull request does is it fully implements those init rules that I talked about with all the different cases of 0, 1, or 2 elements. Makes that initialization consistent everywhere, including subchains of reductions, and that is what fixes many of the dimensional reduction bugs. It's pairwise everywhere. It does the pairwise reductions across all of the different kinds of arrays, the iterators. Skip missing was a challenging one, and actually it ended up being that just treating a skip missing as an iterator was faster than trying to do something special there, which is pretty cool. Because then it can just use it currently uses a specialized MapReduce implementation, but just deleting that and using the generic iterator thing works and just uses its iterator specification and gets the sparse arrays right. It incrementally widens across dimensional reductions. This one is a little tricky and requires us asking the compiler, like, hey, is this type stable? If it is, let's do a fast thing that doesn't do incremental widening. And if it otherwise, we'll fall back to a slower cache inefficient mechanism. It fixes literally dozens of bugs and has some drastic speedups, but also, unfortunately, some drastic slowdowns. This is where my work on this has kind of stalled for now. But this is one of the challenges here, is that this is a hugely generic implementation that affects lots of different kinds of arrays, lots of different implementations. There's size effects, there's element type effects. And so what I ended up doing was just having a lot of benchmarks across all of these different types of arrays and just seeing, how does each case compare to master. So the big tall column there is right around 1, right? It's saying that, we're on par with master. In some cases, we're about 30 times faster than master. In some cases, we're, maybe, 4 to 8 times slower. And a lot of that is because we're missing a SIMD in those cases. When we start talking about non-concrete cases or type unstable cases with any's and small unions, it's a little bit more muddled and the variance is a little wider. But again, we're mostly at parity with master. There's just some long tails that would be nice to hammer out. So where does this stand? We need to make some final decisions on commutivity assumptions and the interface itself. We need to continue working on optimizing it and figuring out the remaining performance regressions, or maybe we call this a fast math sum, or do something like that where we opt in to having SIMD sorts of effects. And really, I need time, because the reason that this has gone away is because I've ended up working on a lot of security related things. And one thing that would help me get back to this is if you come find me here. I want to be working on CVEs and security advisories, so help me get that off the ground. I know we're at time here, but thank you everyone for your time and attention.
Hi, Matt. Sorry that my naive question opens the Pandora box. So in one of your slides, you said that you could potentially increase accuracy by reordering or something, but it's bad because it changes the value. And I don't understand that statement. Like, if it increases the accuracy, well, it changes the value by definition. And I don't see that's a bad thing.
Well, it gets to the exact issue that you filed, right? Like the reason that you filed that issue is because you got a different answer depending upon whether you did the sum row-wise or column-wise.
The problem is that if I use one or the other was different, but if both are the same and highly accurate, I'm good.
Yeah, exactly. But making sure that both are the same is the same problem then, right? Like if we rely on the compiler at SIMD macro, then one of them might be more accurate than the other, and we don't know. Like the compiler has the liberty to do that for us.
Got it. Yeah.
That's exactly. It's the flip side of the benefit.
Got it. Thanks.
Yeah, good question.
I have a somewhat similar question, I suppose. I have a bunch of floating point math, both directly like calling sum and indirectly like calling statistics.mean, which calls sum. And I don't really care about performance. Like I do, but a 2x slowdown is, I mean, that would make me sad, but it would be okay. I don't really care about accuracy. It could be off by a hell of a lot of ulps, and that's fine. What I do care about is that it's consistent. So if I refactor my code and instead of passing a view over an array, now I'm passing a view over an abstract array that I just defined, I want to get the same answer if the elements are the same. Is there any way for me to get consistent results practically now?
Yes, use my branch. The pull request branch doesn't use @SIMD and does the same pairwise splits everywhere, with the exception of index Cartesian splits, because there it is hard to do arbitrary binary splits. You want to split it columns, effectively, like if you think of it just as a matrix, you're going to split the columns into pairs, and then if the columns are too long, you want to split each column into pairs, as opposed to doing the whole array in halves kind of thing, right? And so the pairwise splits on the pairwise reflector branch aren't the same necessarily still. And I don't see how you could really even feasibly do that without just totally throwing away performance.
Yeah, that's totally fine. I don't, that won't be an issue.
But it's a lot closer.
Yeah. Okay, let's merge that then. Thank you.